So I'm happy to welcome Zach Totlock. He is from the University of Washington, our Washington campus, as we call it here. And he's been doing great work in programming languages, and recently by applying programming languages ideas to computer-aided design and 3D printing. And I'm really excited to hear what he has to say. So Zach, go ahead.
Thanks very much, Oz, for the introduction. And exactly like you said, I want to talk today about applying some programming languages techniques to sort of the computational fabrication domain. But I want to start off by acknowledging my many amazing collaborators who did all the heavy lifting on this work. None of it would have been possible without them. So what's on the menu for today? Well, I was hoping we could have sort of a quick 4-course meal. Starting off, I wanted to talk about some motivation or maybe a worldview that underlies this work, which is that everything is a program. We're surrounded by all sorts of consumer goods, and deep down, I'm going to claim those things are actually just code. After that, we'll talk about how to run this pipeline that goes from an idea to a good or a product, a part, run parts of that pipeline backwards. In particular, we're going to focus on going from one intermediate representation called STL, which stands for stereolithography, just a set of triangles, backward to an expression in constructive solid geometry. And then we'll talk about how to keep going backward from constructive solid geometry to CAD, and then talk a little bit about one of the core engines that helps make these techniques work, which is a quality saturation building on this new egraph library called egg that we've been developing. So to start off with, have this worldview that everything's a program. And if you look around, right, like basically probably most products in your house itself, the built environment in general, typically these things begin life as digital artifacts, some specification, which is then transformed by a series of meaning-preserving steps into a final physical object that we use day to day. So I wanted to walk through a particular perspective on that. This is sort of the maker's view or the desktop manufacturing view, but I think this pipeline, this story generalizes. So if I want to go from an idea to a part, to an object, I first need to think about something I want. So I happen to have all these IKEA Allen keys laying around, right? And if you're like me, they sort of accumulate and they get everywhere. They're a little annoying. So I wanted some kind of holder so that I could store them more easily, keep track of them so they won't rattle during talks or whatever. And what I had to do is from that idea first design a program in CAD that represents that object. And in this case, that's pretty easy. It's like, 6 lines of code or something. And you can see in this sort of domain-specific language, we have a few features. We've got geometric primitives like cuboids and hexagonal prisms. We have geometric operators like difference and union, translate. We also have rotation and things. And also, there's this repetition of the holes going into the body to make places for the hex wrenches. And that's represented using just typical programming features like loops, in this case, in sort of a functional style, using things like tabulate and fold. Now, in the real world, most people who do CAD design don't write code like that. In fact, it would probably be some kind of intermediate representation used in some GUI-based tool like Fusion 360 or SolidWorks or Rhino or even OpenSCAD. Now, once we have the CAD, we need to start carrying it down. We want to start removing abstractions so we can get closer to something we can actually manufacture. And the first step on that path is to go from this CAD language to another language called constructive solid geometry. And here, constructive solid geometry is really just a subset of CAD. So we still have the geometric primitives, we still have the geometric operators, but we've removed sort of sugar, right? We've unrolled the loops, we don't have any control flow left, we don't have any lambdas, etc. And we're getting rid of these abstractions, we're getting closer to something we can manufacture, but we have lost something in the process, right? So while the primitives, like the size of the cube or the details of the translate, those parameters are still easy to tweak. If we wanted to do something like add more holes or change the hole spacing, or if we want to change the shape of the holes, that's going to be a lot harder. So we're losing something as we go. Some tweaks are easier though, right? If I just wanted to do a special case on one hole, well, that's easy to reach in and just do it at that one part of the program. Moving on down the pipeline from CSG, we want to go to a lower level representation. This is called sort of a mesh representation. I'm using STL as a stand-in for mesh representations in general. And now we see that things are starting to get pretty different. So we've lost all of our nice geometric abstractions, and instead we're left with just a set of oriented triangles. And by oriented, I just mean, you know, a triangle's a 2D fragment, but it's embedded in this 3D space, and we need a normal to let us know which direction of the triangle represents out away from the object. So we're just going to represent that solid by its surface. Now we have even less editability, right? There's no parameterization. It's basically not human readable. Although there are some tweaks that suddenly become possible once we're at this mesh level, right? Everything's been made fully precise. And so some analyses and optimizations are actually easier here because everything's been made completely geometric. One of the classic examples of this is doing things like topology optimization. So if I want to bring like finite elements to bear to analyze an object and then optimize it based on some specification, like, you know, minimize deflection under a certain load, etc., I want to do that at this level of abstraction. But we're still not able to actually manufacture this. We're still sort of declarative. We're just describing the surface of a solid now. So we have to keep on going down the pipeline. And from this set of triangles, we want to get something we can actually run. And so for that, we typically go to something like G-code. And G-code is just this language. It's flat, imperative. Essentially, it's sort of like a souped up version of logo programming. So for those of you who don't know, logo just lets you sort of move a turtle around a screen, and it can either be dragging a pin or not. And that's basically what G-code's doing, except for manufacturing devices. And again, right, we've lost even more abstraction, not really human readable. There's no loops, there's no control flow. And furthermore, G-code's not even portable, right? So it is semi-standardized, but the details of the G-code semantics tend to be extremely machine dependent. That said, there are people who actually make their living doing things like editing G-code by hand. The gentleman in the photograph is actually my father, who was a machinist for 30 years. And so in his day-to-day life, he would edit G-code, but that makes me feel sorry for him. And so I'd like to make things easier for folks like my dad. And of course, there's still several steps left in the pipeline. These steps are also interesting, and I think there's a lot of interesting programming languages challenges here as well. We have to take that G-code and somehow interpret it. And typically that's done on really low power embedded CPUs. Typically there's no feedback. So for desktop manufacturing, you usually use stepper motors rather than servos, which have encoders in them, so you know the position. So this open loop control, when something goes wrong, we don't know. And time is money. So we want these things to run quickly. And there's a lot of optimizations available. The photo on the right is a recent failure I had where I had a print run all night only to have the filament back up into the printer, and it took me like 3 hours to clean it. It was extremely frustrating. Now, we sort of see this pipeline maybe as looks a lot like a compiler, like a typical programming transformation workflow. But of course, in practice, it's not just one direction. When you get the part out, it's often not exactly what you had intended. And so you roll that feedback back in, and you have an edit, compile, test loop, just like normal programming, although it's a bit slower. Okay, so everything's a program, or the output of a program. And this sort of...
Is that
Oh, yes.
This is Tom. Where does printability fit in? That things have to be connected and that it can be built up in a certain direction that understands gravity and whatnot?
Yeah, so you would probably want to analyze that after the STL level, because that's when things have all been made sort of, just geometry. And so it's easy to answer geometric queries like, is an overhang too steep to print because gravity will cause it to droop too much? But in practice, the tools that people use often don't do those kinds of checks. So it is fairly, it requires some expertise. Like these are things that you just need to ensure when you're, carrying your design through this pipeline to establish. There are papers and there are tools that will try to check those things, but not a whole lot. So there's need for analyses actually throughout the pipeline as well.
Okay, thanks.
Yeah, that's a great question though. So I think there's a ton of opportunity here, and actually that leads into this point. Like, well, why should a programming languages researcher care about fabrication in particular? Like, isn't 3D printing dead? Yada yada yada. And it's true that there was a lot of hype about things like 3D printing, but in some ways we stopped hearing about it because it has been successful, but it's only for people who are willing to put in a lot of effort. One place we saw it shine again recently was actually in response to the early COVID crisis, when hospitals were running out of key materials. People were 3D printing face shields. There's 3D printed masks now. Here's a picture of one of the lead students on these projects, Chandrakanta Nandi. She was printing ventilator filters actually to help with the response. But I think also this domain is really interesting for programming languages because these intermediate representations are both really easy and challenging from a PL perspective. So they're really easy targets because all the programs are typically really flat. The higher level ones are very short. Loops are all bounded. Control flow can be resolved. There's no pointers. There's no aliasing. And the semantics tend to be pretty clean. They tend to be pretty mathy, geometric. On the other hand, there's a lot of hard things that we don't do well in programming languages yet. So while the semantics, based on, 3-space is pretty convenient to do proofs with on paper, actually implementing it is hard because computational geometry tends to be, the algorithms are just very slow and they're approximate. So you're going to hit rounding error in practice throughout this pipeline. Another challenge is that many of the optimizations we want are sort of ill-posed. There are multiple valid solutions, and so they're going to require some kind of search. But most importantly, for me at least, is there's this kind of vision that if we could make these things really easy to use, if we had good tools and things were programmable, we could get away from this sort of one-size-fits-all world we live in where there's a limited set of options of products that you're allowed to buy, that you're able to buy. Instead, you could take things and modify them easily and fit them to your needs. And I think that's really exciting, especially because people who are differently abled often can't find products that work for them, and they're sort of left out in the cold. So this empowerment, I think, for me is perhaps the most exciting reason. Okay, so that's the pitch. That's why we're interested in these problems, maybe where we hope to go. But to dig in a little bit deeper, let's look at a couple of projects we've done working in this space to make things a little more concrete. So first off, I want to talk about decompiling, working backwards from a surface mesh representation like STL, just a set of triangles, to a constructive solid geometry representation where we actually have an expression we can do something with. So why would we want to do that? Well, it turns out that making CAD programs, designing stuff is difficult. People go to school for 4 years and make a living doing CAD design. And when you buy a 3D printer or a laser cutter or a mini CNC mill, typically you just want to download stuff and print it, right? You don't necessarily want to have to become a CAD expert to use these machines. So if we look at the pipeline and ask ourselves, okay, well, what should we share so people can just download and print? Well, the challenge is that the low end of the pipeline is too machine specific, right? As we mentioned, G-code, even across different 3D printers, needs to be tweaked for that printer. So if I share the G-code, I'm not going to be able to, it won't be useful to many people. At the other extreme, the front-end tools are also, the higher level IRs are also not really appropriate because they're very tool specific, right? So maybe I designed my model in SolidWorks, which is a really powerful CAD suite, but it costs, thousands of dollars a year for a seat. And a lot of end users aren't going to pay that for CAD tools. So if I share these higher level representations, people also won't be able to reuse it. And so we're left in this kind of Goldilocks situation where the obvious choice is right in the middle, neither too abstract nor too concrete in these surface level triangle mesh representations. And there are a lot of repositories. Maybe the most well-known is this one called Thingiverse. And there people share these STL meshes so that others can download and just print them. And that's great because it's easy. But if you can't find exactly what you want, you're sort of out of luck. And maybe more frustrating is that often you'll find something that's almost what you want. But because it's in this STL representation, you've compiled away all the higher level abstraction from the program, and so it's really hard to edit it. It's really hard to tweak things to get what you want. So in the case of the wrench holder, I actually went to Thingiverse and I found some wrench holder. It was in STL, and I printed it, and sure enough, I got a wrench holder. But the problem was one of my wrenches, these are like IKEA wrenches. They're very inexpensive. It was incorrectly manufactured, so it wasn't bent the same way as the other ones, and it didn't sit square. Now, of course, that works, right? I have a wrench holder. I can put the wrenches in it. But being extremely type A, this really bugged me, right? And I wanted it to sit square, but it's really hard to edit the STL to just rotate that one little hole to get what I wanted. So what did I do? Well, I loaded up the STL, and then I manually reverse engineered the program into a CSG program. And then I could easily just add a rotation to one specific hole. And that allowed me to print the holder and get what I wanted, where all the wrenches set square to each other, and it's not nagging me, keeping me up at night. So that's the goal of sort of this phase of the project of the talk that I want to talk about. We want to be able to take these widely shared representations and decompile them back to constructive solid geometry so that they're easy to edit. So how are we going to do that? Well, to decompile, it's usually helpful first to understand what the heck compilation is doing. So we're going to roll up our sleeves, put our PL hat on, and dig through some classic syntax and semantics, but applied to this more geometric sort of CAD domain. So we can make a little DSL for our language, and it has several features. So one second, I'm gonna get some more water. In particular, there's some notion of a mesh actually in our CAD language, and that corresponds to sort of values in this language, right? So compilation should take a CSG program and grind it down into a mesh. We have various geometric primitives like cubes, and cylinder in here means sort of an insided cylindrical prism. We also have affine transformations that gets us things like rotation, translation, scaling, etc. We can add sugar to make those a little bit easier to use, but really they're all just affine transformations. And we also have sort of more set theoretic operations like union, intersection, and difference. Right, so the language is pretty small and clean, and it's not too hard to give it a fairly natural semantics. So in particular, we can just denote our CSG programs directly to the set of points they represent. And this denotational semantics is really useful when I want to reason about programs, because now I just have to think about sets of points. One subtlety is that I do need to be careful about keeping the sets regular open, so that I don't end up with sort of infinitely small holes in objects, right? So I need to think carefully about the boundaries, especially for the binary operators. If I have two regular opens that are infinitely close, when I union them, I need to make that one solid. So there's a little bit of subtlety there, but basically semantics just work how you want. And they bottom out here with the mesh semantics, and that's just given by ray casting. The details aren't super important, but at a high level, you sort of pick a random point, you cast a half line, you cast a ray out of that point, and then you count the number of triangles in the mesh you cross. And if the number of triangles is even, then you are outside of the mesh, and if it's odd, then you are inside of the mesh, right? So pretty simple stuff. So we got this semantics, but it's a little bit too big step, right? It just reduces a program down into a set of points, and it doesn't really give us hints about how we might build a synthesis procedure. So what we're going to do is we're actually going to, inspired by the semantics, try to break it down into smaller parts and build, fairly traditional small step operational semantics for it. So as the ancestors taught us, when you want to write small step operational semantics, you should probably first get some evaluation context. So this is just describing, this is just giving holes, like where the action is in a term where the red X's can appear. It tells you what to evaluate next. Armed with evaluation context, it's pretty easy to give the semantics. So primitive steps, just say if you can find a red X, then and you can step it, then you can take a compilation step as well. We have primitive steps for the geometric primitives. In those cases, you essentially just, you have the primitive and you just directly generate the mesh for that primitive. And for the affine and binary operators, because we set up the evaluation context just right, we know that when we step those, their arguments will always be meshes already. So in those cases, we just need to call the underlying sort of mesh library to do the mesh level operation on those arguments. And this semantics is really simple. It's deterministic, but being with horizontal lines and stuff, it can be sometimes a little bit difficult to envision, like, what does it mean to run the semantics, to compile something according to these rules. So let's look at a quick example. So here we have just the union of a couple of cubes. One of them's translated a little bit over to the right. And, to compile it, we first, so I have a binary operator. I first need to compile it on the left-hand side. In this case, the left-hand side is just a cube. That's a primitive. So that just turns into a mesh. I'll take some more steps. I'll replace that mesh. I have a new evaluation context. Now I need to compile the translation of a cube. I take some more steps there. I need to do the mesh of the mesh level translation of the cube mesh, et cetera, right? So, and eventually we'll grind it all the way down and just have one mesh left, right? We've reduced the program to its value. We've gotten the triangle mesh out of the constructive solid geometry, or we've gotten the, triangle mesh out of the constructive solid geometry program. And the intuition here is that it's pretty simple, right? You find the next place you can make progress, you compile that thing to a mesh, and those meshes sort of bubble up the AST, and I just do mesh operations as I go up. Whew, okay, so we've got compilation, but again, the whole point was to get decompilation, right? We already know how to go from CSG to STL. There's a billion tools out there already. People have implemented this since the 70s. What about going backwards, right? That's something people haven't done before. So the intuition here is actually really easy, right? We saw, like, we have this path from the CSG down to the STL. Now we want to go backwards. So why don't we just flip the arrows, right? I want to search backwards through that graph to try to find a CSG program that would compile to the mesh representation. So doing that, visualizing that in terms of our example, I want to, take a path like this and just flip all the arrows, right? I want to define another relation, sort of a synthesis small step relation, and, work backwards to some high level CAD that will compile to the triangle mesh I was given. And so, we just flip the order of things. First, we're going to guess some way to decompose the mesh. Based on what we guess, we'll realize that decomposition with some CSG operator. And now, instead of pushing meshes up the AST, we're going to push them down the AST. So we'll start with a mesh, then we'll have some operator that has meshes as children, then we'll decompile those meshes, right? And we'll go the other way to decompile it. And that actually comes out pretty cleanly. We can write down sort of this small step relation for synthesis. And each part corresponds to the inverse of the compilation relation, right? So first you need to focus on some promising part of the mesh you haven't decompiled yet. You need some way to recognize primitives. So if the mesh you have corresponds to some primitive, you just want to produce that primitive. There are computational geometry algorithms for doing things like this, or, well, statistical techniques like ransack that are useful in computational geometry. And we also need some heuristics for the binary operators, but we can parameterize all these by geometry oracles that help guide that search. So in practice, this works pretty well. We'll see some examples here in a second, but there are a lot of challenges. In particular, you might be wondering, like, wait a second, like, this problem's ill-posed, right? There are many programs which compile down to the same triangle mesh. And there's also a trivial solution, right? Like, I could let the synthesizer just make a bunch of sort of tetrahedron to represent the surface of the triangles and just union them all together, right? So I could make a CSG that is in some sense no more editable than the triangle mesh I started with. So we really want to treat this as an optimization problem. We want to find the smallest CSG program that produces the triangle mesh. And there's more details about that in the paper, but I did want to talk about sort of 3 high-level challenges that I think are worth mentioning here. So one is that the compilation process loses information, right? So in general, you actually don't have enough hints in the triangle mesh to figure out what you need to do. The other is, how do we make these geometric heuristics, right? We have these geometry oracles. That just seems like magic. So what's the intuition for how those might even work? And the third is that, the space explodes. So we have unlike the compile semantics, which was deterministic, you always knew exactly what to do next. When you're working backwards, you have to search. It's not clear in general what the right next move is when you're trying to work backwards through this synthesis path. So for each of those things, we have a few tricks that help out a lot. My favorite is actually about the loss of information. And this is just one of these really beautiful things that sort of fell out of the sky into our laps. But it turns out that using the evaluation context in the semantics was crucial, because the evaluation context represents the context. Oh no, did I miss you guys?
What happened? Everything came back, but we lost your screen.
Oh, 1 second. It just said.
For me, it stops for like, I don't know, 10 seconds, 20 seconds.
Oh, okay. Let me try that again. Let's see, desktop 1. Oh no, it's not sharing screen. Why? Sorry, friends, I don't know what's going on here. Okay, how about that? Can folks see the screen?
Good.
Yes.
And I lost people on challenges?
Yeah, just before that.
Oh, just before that? Okay.
Yeah.
Let's see. Okay.
Actually, Zach, I have a question. This is Tom.
Yeah.
Like in decompilation of machine code, there's this issue that like an optimizer can step in and kind of smear the primitives or the low-level instructions that came from one higher level statement. Do you have that issue that things can get kind of smeared out? And so
yes, absolutely. Like that's going to be a huge pain. Well, that's a motivating challenge for the next part of the talk. As sort of the part 3, but absolutely that happens. So in case anybody wasn't following Tom's question, and to make sure I understand too, when I start with the source level program, maybe I'm going to optimize it as I compile it. But then when I try to work backwards, I might miss, it might make it more difficult to recover that high level structure, because maybe I did some inlining and some partial evaluation, and I no longer see the sort of patterns that should unify things in the program to make it simpler at a high level. Is that right, Tom?
Exactly. Yeah.
Yeah. So that's going to be a huge problem, absolutely, in the next phase. And we'll see. I think we'll see a quick example of that when we get into that. But absolutely, that totally happens. So we've set the stage. We have this intuition about how we might get a synthesis procedure just by flipping the arrows, but some challenges arise. One is that we, lose information as we compile. There might not be sort of enough hints left in the triangle mesh to figure out exactly what we should produce. We have these geometry oracles that, just seem like magic. So where do those come from? With the intuition for how you might build one. And unlike the compile semantics, the synthesis semantics aren't deterministic. So we're going to have to do some search. So I wanted to just really quickly give some intuition about how we address these challenges. My favorite by far is dealing with the loss of information. So it turns out that the evaluation context that we use in the semantics precisely captured the geometric context in which you're trying to infer a CAD program to replace a mesh. And this is extremely useful, like we see in this sort of snowman example here in the upper right, that if I'm trying to infer some CAD for that red sphere, well, if I just was looking at the way it appears in the final mesh, it's a harder problem because I need this sort of truncated sphere. But if I know the context that I'm trying to infer some CAD in particular that it's going to intersect with this other sphere, then I can produce a much simpler program because I know that it's going to, the error, the noise in it is going to get unioned away. And that makes, suggesting using a sphere for it a really, high scoring candidate. So this way evaluation context showed up. It just sort of fell out of the sky. One of my favorite things about this project. On the geometric heuristics side, there will always be more heuristics you can find that will work for different kinds of objects better than others. Some really easy ones are, look for convexity changes in the mesh. So that works really well with the snowman. It suggests you should split, between the parts of the sphere. There's also easy ones like, if you have a complex shape, you can bound it with different primitives and then look at the difference, right? So you can, you have this primitive that bounds it. You know how to generate the CAD for the primitive, and now you're left with smaller, simpler problem of inferring the difference. Or sometimes you can split models apart just because they're separated by space. And again, you sort of reduced it to a smaller, simpler problem. And in terms of the blow up, we do kind of like a beam search. But one thing that's nice is that this is embarrassingly parallel. And there's a bunch more challenges as well discussed in the paper. In particular, dealing with computer arithmetic becomes hard when you want to implement a practical tool to do these kinds of things. So we did some exploring on exact real libraries. But does it work? Well, we built this tool, Reincarnate. Chandra wrote like 50,000 lines of OCaml to put it together. And sure enough, we can actually take STL meshes from Thingiverse and recover constructive solid geometry programs that compile back to the same thing. So step one done. But it turns out that that's not all you might want, right? So we have made a lot of progress. We've moved from just being given a set of triangles that represents the surface of an object back to an expression that represents the solid object itself. But again, right, those expressions are really flat. So if we think back to this example where we had, a hex holder, what if, there's a bunch of changes I might want to make that are still hard in constructive solid geometry alone, right? What if I want to change the shape of the hole? What if I want to add more holes? What if I want to change their spacing? Like all these kinds of things are difficult in constructive solid geometry because I don't have abstractions to represent iteration or relationships between variables, any of those sorts of things. So this is where we're going to get more into Tom's question about how to address what optimizations might have messed up for us. But to do that, we're going to need a little bit wider aspect ratio because some of the graphs are going to be pretty wide. So let me switch over to 16 by 9 rather than 4 by 3. Okay, so here's another model. This one's an example of a ship's wheel, and it's parameterized in a few different ways. One thing that's really easy is I can change the number of handles on the ship's wheel. I can change their length. I can change how far they're separated apart, etc. And we could take the STL for this and recover the CSG. And it turns out that since we wrote Reincarnate at ICFP in 2018, there have been several other papers that have also done similar kinds of decompilation with different strategies. Some of them based on more enumerative synthesis, some of them based on machine learning techniques. But all of them have this great benefit that you can take a huge STL program and generate a much, much smaller CSG program. However, they don't really do anything for repeated structure, right? So if I want to change the hex holder or the ship's wheel, the problem is I have to go make a bunch of related edits throughout that CSG program. And that's really tedious and error prone. So to sort of try to go a step further and recover more abstraction, particularly for the case of repeated features in designs, we built this tool called Solinsky, which takes a constructive solid geometry program and generates a parameterized CAD program. And the idea is that I can shrink this program even further. We added these features like combinators that basically represent loops. And by getting that smaller program, a lot of edits become much simpler, right? I just change a few characters. I can get very different models that are useful in different ways. So our goal is to take the CSG, infer the folds, maps, and tabulates. And we believe that by doing this, we're going to be able to shrink the program a lot, and that those shrunk programs are going to be a lot simpler to edit. So let's suppose that our mesh decompiler, remember there are several different mesh decompilers now, let's suppose that it gave us just really beautiful input. So if we had this program, let's see how Selinsky might work, where everything's really nice and uniform and laid out with a lot of sort of obvious repetition. One little note about syntax here. I'm going to talk about operators like union as if they were in-array, but in practice they're actually binary, and we'll see why that might cause us trouble here in a little bit. So at a high level, Selinsky works just by term rewriting. So the first thing we're going to do is notice this pattern that I have a bunch of nested unions. I can apply a rewrite sort of over and over and pull all those unions into a fold of the union operator over a list. The next thing I'm going to want to do is notice these patterns. Like here I have these rotates, right? And they're all in sequence, but they all have the same structure, right? So I have a rotate of a translate of something. So I can pull that rotate out. I can do map2 of rotate. I can pull the first arguments of rotate into one list and the second argument of rotate into another list. It turns out I can do that again because I have this list of translates all on cuboids. So I can pull, I have another map2 where I'm doing translates of all those arguments over cuboids. Now what's nice is I've pulled the sort of related arguments to nested operators all into a single list. And now that I've gathered those arguments up, it's pretty easy to ask a solver like, hey, can you find a pattern that repeats across the arguments of this operator? And for us, we built a few solvers, but they're all actually pretty simple. A lot of them are just doing like basic regression. And for many repeated designs for the things people produce on 3D printers, laser cutters, etc., they typically have linear or circular repetitive patterns, sometimes nested, sometimes it's sort of a square, like a grid-like pattern. But these are all things that you can find really easily statistically. I think our longest solver is like 30 lines of code. So really simple solvers. And then after that, we can do a few more rewrites and end up with this target program we had, which has pushed the tabulate back out of the map2. And so we end up with this 1, 2, 3, 4, 5, 6-line program that is much easier to edit again, and we can get that kind of flexibility that we saw at the beginning of this segment. So I want to just really quickly talk about each of these phases. Let's just we'll zip through these because I also want to talk a little bit more about egraphs too. So the first thing was this structure finder, right? So when I see this sort of sequence of the same operator, maybe with different arguments being applied over and over, I can turn that into a map2. I can pull that out just by repeatedly applying the right rewrites. In this case, I'm going to do it for that map2 rotate like we saw. And I can also do it again for the translate. Once we've pulled things into those map2s, then we have this ability to ask solvers to find patterns in the parameters to the operators. So we can, figure out like, oh, well, this should really be some kind of a loop that's doing, a slightly different thing, the same thing on each iteration parameterized by its index, right? So the first one will be 0, the next one will be 60, the next one will be 120, on and on up to whatever 6 times 60 is. What is that, 360 or something? Okay, so that gets us pretty far. And if we have this ideal input, it turns out that this approach will work. But the problem is exactly what Tom was just talking about. In practice, the CSG programs produced by decompilers are not ideal, right? So they have all kinds of challenges in them. In particular, a big one is just ordering, right? Because remember, the decompiler is just trying to go from the raw geometry, from the triangles back to an expression. So it has no idea at a high level what order the parts of the program should appear in in order to facilitate getting higher level abstractions back. So in practice, I'm going to have all kinds of things reordered. I'm going to have transformations that are semantically equivalent but different. So like here we have this rotate that corresponds to a translate. Here we have a rotate that corresponds to a scale. And it can be really hard to try to see the high level structure when the program's been all permuted in this way. And because of that, our previous strategy of just applying some, particular fixed sequence of phases, like do these rewrites, do some structure finding, apply the solver, do some more rewrites, ain't gonna cut it, right? The things that come out of the mesh decompilers are sort of too permuted for that to work on many examples. Instead, what we have to do is we have to interleave rewriting with structure finding and the custom solvers. And the question is how to do that, right? Any one order we pick will be pessimal for some example. So we have this sort of phase ordering problem that you classically see in a lot of people optimizers and other rewriting-based program transformations. But we had this old technique from like a decade ago called equality saturation that was meant exactly to address phase ordering. So we were curious, like, can we apply this in the context of fabrication? And spoiler alert, it turns out that it works pretty well. In particular, what we want to do is be able to find these equivalencies so we don't treat programs that are really equivalent as different. So the way this works, if we represent the program on the left as an egraph, we have a few things here. We have these E-classes. Those are the lightly dashed boxes. E-classes contain E-nodes, and each E-node represents some operator. And what's important about E-nodes is that the child of the operator is not to other E-nodes. It's to E-classes, right? And in this way, we can represent many equivalent programs really efficiently. So if I treat that equation at the top as an equivalence, if I use it as a rewrite, I can represent both programs in the same egraph really efficiently. And I get a lot of different ways to express the same thing in that top root node. Now what we're going to do is we're going to be running the egraph, and as we go, try to find opportunities to do structure finding and apply our custom solvers. So if we take our running example and we stick it in the egraph, we from the structure finder learn this thing about the map to and rotate. So we have that in the egraph. There are also some additional cat arguments to map to. I'm not going to show here for space reasons. But now I have this list of the parameters to the rotate. I can chunk those into a really simple solver. Look at that. You can see the pattern. It's obvious. No problem for the solver. The solver can easily turn that into a tabulate, and boom. Now I've recovered a loop for the program. I know that this tabulate is equivalent to the list that it generates. I can unify those. I've recovered the loop. Everything is hunky-dory. Now, you should be a little bit suspicious though. This is, at a high level how it works, but the problem is that that list we gave the solver was sorted. And we just got done saying how these decompilers can produce their, resulting program in any order, right? So this isn't going to work in general. So how are we going to handle things when the program we start with, has arbitrarily reordered sub-expressions? Well, if we, just take this approach where the arguments of the solver are in order, the solver's not going to be able to find a nice closed form tabulate that works. Instead, the solver is going to have to sort things to find that clean loop that expresses the pattern, that iteration that you want. But if we let the solver sort its arguments, well, then we're in trouble because the tabulate we produce is actually not equivalent to the list, right? The tabulate is going to produce things in order, but the list we gave the solver was unordered. And we can't merge those in the egraph because they're not equivalent, right? It would be unsound and you get all kinds of things go wrong once you have 0 equals to 1, basically. So one thing you might think is like, well, we got these rewrites. Maybe we can say that a list under a fold union, we can permute it. So we could just try to add all the permutations using sort of associativity and commutativity. But unfortunately, that blows up real quick. And this is a classic problem from the automated theorem proving community. known as the AC matching problem, or associativity commutativity matching problem, which just makes it really hard because there are exponentially many equivalent terms once you have associative and commutative operators. So we did something slightly different. Instead, what we're going to do is we're going to let the solvers tag their results. So we're going to let the solvers do things like sort their inputs, but then tag the results saying, well, this would be equivalent if it showed up in a context where order didn't matter, for example. So, you know, more concretely, in general, suppose you ask the solver to solve some query A, but it can't do that. Instead, you know, it can solve a related problem. So what we're going to let it do is sort of tag its solution with the inverse of the transformation it made to make the problem solvable. And then we'll see if we can cancel that inverse transformation later using more rewrites in the egraph. So the way that looks in this example is, you know, we're going to start with our program. We're going to apply the structure finder. We're going to find this list. It's unfortunately not ordered, but, you know, we'll be able to go ahead and give it to the solver. Now the solver, again, like we just said, it can't unify it, but what it can do is it can say, well, hey, if you unsorted according to the permutation it used to find a solution, then the output would be equivalent, right? So the solver is going to tag its result, the loop it produces, with the sort of inverse permutation that would recover the original input. And now we can actually propagate that through the egraph, right? Now the unification is sound. So by letting solvers tag things with the inverse transformation, you still get the sharing that egraphs provide. And you can sort of chug along. And now what happens, of course, is we have these unsorts, you know, tagging solver results that are flowing through the egraph. But what's great is that additional rewrites are going to be able to simplify those away. Because, for example, in the context of a fold union, get there real quick. In the context of a fold union, a sort of unsort is an identity, right? And so that sort of cancels via rewriting, and you end up with the target high-level program. So we think this is a technique that we can probably use in a lot of different domains. It allows you to flexibly combine solvers that need to do things like care about order, which egraphs are bad at, with the things that egraphs are good at, which is propagating rewrites and not worrying about you know, rewrite ordering. So it turns out, you know, we implemented this. We ran it on the output of reincarnate, and we got huge shrinkages. So we got much smaller programs. You know, it sort of recovered the repetitive structure in the program. Of course, that's just our own tool. So, you know, we would like this to be useful to makers and fabrication, like people doing fabrication in general. So we went to Thingiverse. We downloaded a couple thousand programs from the wild, and, you know, decompiled those. And for, you know, this is sort of separated by size. So when the input program is really small, there's not much to shrink. But the larger the program is, the more you can shrink it. So we're able to shrink, you know, the large examples by around, you know, nearly 80% most of the time. And what's really nice is that all of these, you know, recovery of abstractions, this re-rolling of loops, we did all of these examples each in less than a second. And there's sort of a gallery of different stuff, you know, showing how that works. You get these small programs, these different patterns. So the implementation's about a couple thousand lines of Rust. Please check it out. And you know, what made it really fast was this new library called egg that's specialized to equality saturation. So let me switch back really quickly to this other deck. I know we are short on time. So I'll just zip through a couple things real quick, but would be happy to hang around and talk about more. Of course, there's more about Selinsky in the PLDI 2020 paper. And I guess I should mention Selinsky's a homage to an 80s film called Honey, I Shrunk the Kids, whose protagonist is, his last name is Selinsky. And we're, you know, shrinking programs. Okay, so at the end, we mentioned Selinsky's fast because this egg library. Egg is designed to help with equality saturation. The you know, equality saturation workflow is basically what we saw in Selinsky. You take a program, you put it in an egraph, you apply a bunch of rewrites, and at the end, you can find a sort of a best term in the egraph that you can extract. A lot of times it just means the shortest representation. That's what we use in Selinsky. Yeah, so the heart of this approach is really the egraph, originally developed in the automated theorem proving community to help with congruence procedures. And that's important for representing many equivalent terms. Essentially, when reasoning, if I know that A is equivalent to B, then I know that F of A is equivalent to F of B, and I need to propagate that information efficiently. So quality saturation repurposes the egraph for program optimization. It's a nice algorithm. It's like 10 lines long. It's pretty extensible. I can add domain-specific rewrites. I can use a domain-specific cost function for extracting the best program. And one thing that's really nice is that it's potentially complete. If you actually saturate the egraph, right, if you go through an iteration trying to find additional rewrites and you don't find anything new, what that means is that you found every equivalent representation of your input program with respect to the rewrites you're using in a quality saturation. And then if you select the best one from that, well, you actually have a guarantee of optimality. And there's more about this approach in our Popple 2009 paper. But we sort of worked on other stuff for a while, and we came back to try to use a quality saturation. We noticed some pain points that prevent scaling. So one thing is that the reason equality saturation doesn't have to worry about phase ordering is that when you apply rewrites, nothing is destructive. You never lose information in an egraph. But that means that it gets really big. So we need to figure out how to scale. But there are some things that we can do differently from SMT solvers. SMT solvers speculate in order to run DPLL, right? They guess satisfying assignments, and sometimes they guess wrong. And when they guess wrong, information they added to the egraph has to be rolled back. For a quality saturation, we never make mistakes. We don't need those capabilities. So how can we make a quality saturation, egraphs better for a quality saturation? Well, the bottleneck, as you might guess, is congruence. That's the whole point of egraphs. Here's an example. If I have two E-classes that have an E node that has the same operator and their children are the same, well, I should merge those. So this violates the key congruence invariant you want your egraph to maintain. And so what you have to do is you have to search the whole egraph for those and find opportunities to merge them. Once you put them in the same E-class, then you can dedupe them really easily to make sure your congruence and, it says dedupe invariants are restored. So how are we going to specialize egraphs to a quality saturation to avoid this bottleneck? 2 steps. Step 1, turns out that the equality saturation workload can be split into phases. Rather than maintaining those expensive invariants every iteration after every time you rewrite, instead you can split equality saturation into phases. In one phase, you find all the matches that you can currently find in the egraph, so it's read-only, right? And in the second phase, you can batch all the modifications. And what that does is it amortizes the invariant maintenance. So you need to do congruence restoration less often. And so that provides a big speed up. The second part is a new algorithm for restoring those invariants. So we have a very simple work list algorithm that uses all cache-friendly data structures. And that's possible. We can use these sort of flat vectors because we don't need to roll back. So egraphs in SMT solvers, again, right, they might make mistakes and have to undo things, so they keep a lot of pointers. There's a lot of pointer chasing, but we don't have to do that because we never make a mistake. So the question is, if we split equality saturation into phases, and we use this new rebuilding algorithm for restoring invariants, do we get any benefit? So here's a graph comparing, using rebuilding once per iteration and once for every merge. And lower is better. So you can see that we basically have a flat line. So compared to doing it after every rewrite, it's almost constant. Now this is a little misleading because the scale is linear, but even when you put it on log scale, we see that there's significant speed up. There's also evidence that it's a super linear speed up. So the more rewrites you have, the further you get into equality saturation, the bigger the win from phases and rebuilding. We also did a case study, aside from Selinsky, applying this in Herbie. Herbie is a tool to automatically improve rounding error, relies heavily on simplification. We took this sort of phased approach and the rebuilding algorithm and got huge speed ups in the Herbie implementation of egraphs, like a 50% speed up. Egg has additional optimizations I don't have time to talk about, but it is much, much faster. That's log scale there. And furthermore, because it's so much faster, it can get deeper into the search space and actually produces better results. There are other uses of Egg. For example, optimizing linear algebra code for machine learning using relation algebra. This is at VLDB 2020. So this, Egg is really fast, and by being specialized to a quality saturation, it provides huge speed ups and makes new things possible. So we're really, really excited about Egg. But wrapping up, we sort of had this 4-course lunch. Everything's a program, compiling backwards from sets of triangles, just raw geometry, to expressions in constructed solid geometry. Those are noisy though, so how do we recover high-level structure like loops for repeated design features, using a quality saturation? And then finally, how do we make it fast? And we do that by splitting a quality saturation into phases and using a new invariant restoration algorithm. So just wanted to once again thank all the amazing collaborators that made all this work possible, did all the heavy lifting. If folks are curious, all this stuff is on the web. Please do check us out to learn more. And with that, I think I will end the talk. Thank you all very much.
Thank you. Very nice work.
Thanks a lot.
I have a question. I'll start since I'm the host, so I can do whatever I want. Have you looked into applying similar techniques to things like music, like reverse engineering the wave file into like a Sonic Pi script?
I love that problem. We've talked about it over dinner. Well, back when people got dinner together, but nobody has done it yet, as far as I know. There's quite a lot of machine learning work on decompiling music, like taking classical music and trying to decompile it back to sheet music. I think you'd have to compose with that somewhat, because the analog of for the 3D modeling world, we had these sort of geometric oracles. And so the analog of that for music is you need some way to extract the different instruments. And so you need some of those machine learning techniques to pull out the sort of parts of a song. But once you have that, then you could think about, well, from that signal, can I produce the notes? And then from the notes, can I find things like repeat this measure or something? I think it should be doable, but I don't think anybody's explored that yet. I think it'd be a super fun project.
Yeah, definitely.
This is Tom. I have another question. It seemed like what you were doing with egraphs and inserting the sorts and unsorts was is that related to second order unification, or is it a special case of second order unification where you're biased to the functions being sort and unsort?
That's a good question. So I'm not totally sure. Can you remind me like the setup for the second order unification problem? Is it like under some?
You're basically allowed to put in beta expansions.
I see. So if I sort of ran the fold union, if I knew the context in which the unification was happening, then that would allow it. Is that the intuition?
It's just, I guess, the way I've seen it, years and years and years ago, there was a paper by Bernard Lang and Gerard Huet on second order unification as a primitive in a programming environment, because you could do AST matching better. I probably have it mischaracterized because it was a long time ago that I looked at it, but it's something like that. And then they phrased it as the general second order unification problem. And Huet he sort of went off the deep end on higher order unification, and eventually you get to undecidability results. So I think second order unification can be costly, but they, even with the slow computers of 35 years ago, they were able to do something with it.
Yeah, I just made a post-it. I'm gonna definitely follow up on that and ask students, and I will report what we figure out. That does sound promising.
Oh, okay.
All right, any more questions? Okay, I guess we should thank Zach for joining us, and hopefully next time we'll have him in person in Madison. I
Yeah,
hear he's from the
fingers
Midwest, so.
crossed. Thanks, everybody. It's good to see you all.
Thanks, Zach. That was a really terrific talk.
Thank you.
Thank you very much.
Thanks a lot,
Thanks
Zach.
very much.
Bye.